This is CS50 week 11, so we have an amazing lineup for you today. 8 computer science faculty from 8 different fields, from 8 different courses, toward an end of giving you a taste of what computer science is beyond CS50. It's perhaps unfortunate that a lot of you enter college having had the experience in high school of seeing a fairly dry curriculum. Hopefully that we have sexed up just a little bit here, but it's also the case that in society, too many people don't quite understand what computer science is. In fact, they conflate it with either programming as a profession or as IT itself. It's perhaps apropos that one of your classmates posted this to the course's bulletin board just this morning, a commentary on something he or she saw on a popular website. Your classmate commented, because what they saw, so this is not, in fact, computer science here. So what you do have today is, in fact, the real computer science. 8 different faculty to give you a sense of what is beyond CS50. And just as a more personal anecdote, what was really exciting for me at the tail end of CS50 all those years ago was to see how many different directions one can go off in. And these days, now that minors exist, with just 3 more courses after CS50, can you actually call yourself a computer science minor, or with a few more, a computer science concentrator? So our first guest today, Professor Greg Morissette, from Computer Science 51.
Thank you, David. What's 51 about? So 51 has some fancy title that I can never remember, like Computer Science 2. But it's really about programming at the next level. So all of you at this point know how to program. It's actually not that hard. I've been teaching 5th graders how to program for a long time. It's not that hard. What's really hard to do is to program well, okay? How many of you have encountered the blue screen of death? Yeah, okay. How many of you have encountered another bug in software? How many of you have encountered security failures or breaches? Okay. So these are all symptoms of basically physics concentrators going off and working in the computing industry without proper training. So, no, just kidding. So I, who depend upon the software that you guys are going to write, that is to run my car, the airplanes, the banking system, everything, I want you to be able to write code that is reliable and efficient. Because I'm also a developer, I want it to be readable and maintainable. I want, in fact, that you should be able to reason formally about your code. For example, you should be able to reason that the data structures that you're using are implemented correctly. And most of all, I want some elegance in the code. Okay, so the goal of 51 is to provide some tools that take you further down the road of writing excellent or elegant code, and to also increase your problem-solving skill set, okay, by introducing you to new languages and new abstractions. So another way to think about 51 is it's sort of what I call software engineering in the small. So the focus is on a set of tools, abstractions, and techniques that you can use when you're coding to do a better job of assembling software. Okay? It's not software engineering in the large, because that involves the team components of software engineering, which is very hard. There's a little bit of team programming in 51, but not at the scale that you'll find in big companies like Google or Microsoft. Okay? So along the way, we're going to introduce a whole lot of programming abstractions. You can see some of them up there, like polymorphism or inheritance, synchronization patterns, and so forth. We're also going to introduce you to certain elements of engineering design. So we're going to be looking at things like coding style. So 51, you get points taken off if your code is ugly. All right, it has to be beautiful, something you want to take home to your mom and show her that. Okay, so you really want to polish the code. We're going to be talking about interface design. We're going to be talking about efficiency concerns, both in terms of space, time, and these days, increasingly power. We're going to learn to analyze, think, and express solutions to problems with precision. And really, that's the advantage of studying computer science, is that these problem-solving skills pay off in other domains besides software, any domain where you need to be able to formulate problems and think about them precisely. Okay, so who should take the course? Basically, all of you. Okay, no, seriously, if you're going to major or minor in CS, I think 51 is a great course. It is really a gateway to a lot of the upper-level courses that you'll hear about later on. 61 is also really good, and in fact, I think the new requirements in the concentration say that as long as you take 2 of the 3 amongst 50, 51, and 61, the CS faculty are happy, although I think ideally you should take all three of those. Okay, they really give you a firm foundation. 51 is about building up, programming abstractions. 61 is about understanding those abstractions all the way down to the metal, and Steve will talk more about that later on. I think 51 is very important, not just for CS concentrators, but also fields like electrical engineering, applied math, biology, finance, economics, and so forth. All those disciplines have been revolutionized by computation. And you can't be a first-class member of those kinds of disciplines without having really good computational tool sets. I also think that the kind of emphasis that we do in the class on design is really important for those of you who have an entrepreneurial spirit, that is, formulating problems and getting precise solutions to them. Okay, the only background that we require is CS50. It does help to have a little bit of mathematical sophistication, but you don't need a lot. Okay, so the course uses two different programming environments. The first one is called OCaml. How many of you have heard of OCaml? Wow, 3 people have. 4, 5. Okay, good. All right. So it's a very strange programming language that most of you have never heard of. But for example, Microsoft just released a new language called F# that is derived from OCaml. And they're basing a lot of their development around that functional programming language. So ML is in the functional family of programming languages. Part of the reason we use ML is because it's going to stretch your mind in the way that you think about how to formulate problems and solutions. And I'll give you an example in just a second. The final third of the class will be talking about Java, and in particular object-oriented programming and design patterns for successful object-oriented programming. We'll talk a little bit about concurrency at that time too, which is very important these days. All right, so why do we use these two different programming environments? Part of the reason is that language, the way you formulate thought, matters when it comes to algorithms. And my favorite example is that one up there. Suppose I gave you a homework assignment that said, try to write a procedure, a routine, that will multiply 2 Roman numerals. That's really hard to do. I don't even know how I would write that code, except to maybe translate the numbers back into Arabic notation, right, decimal notation, and then do the multiplication there and then translate it back. Right? But doing it directly on the Roman numerals is hard. So if you can only think in one style, like Roman numerals, certain algorithms are going to be out of reach for you. All right? If you can pick the right language, the right abstractions that suit the problem at hand, then you can formulate a solution and you can do the translation back to the environment in which you're forced to work. Okay, so just to give you a little example, one of the data structures that we're going to study in 51 is called a red-black tree. It's a balanced binary tree that supports efficient lookup, insert, and delete. All right, if you look in a standard algorithms textbook, the code for just inserting an element into a red-black tree looks like this in C. Okay, so you don't really need to look at the details of it, but that's a quarter of the code. There's another quarter of the code. So you just saw half the code, and the rest of it is symmetric. Do I have this code right? It turns out there's a very subtle bug in this code, which the students in 51 last year discovered. Okay, and it's very hard to recognize it. On the other hand, if you code that same function in ML, it looks like this. So first of all, it fits on a slide, so we can start to actually formulate the algorithm in one slide and think about it. It looks a lot more like pseudocode in a certain sense, but it uses features like pattern matching, higher-level data abstraction concepts like algebraic data types that allow you to think at a much higher level of abstraction, formulate an algorithm. Now, sometimes what you need to do is take that code, formulate it, test it in an ideal environment, and then translate it back to this god-awful mess of conditionals. All right? But oftentimes, you can get away with working in a more sane environment. I'm not saying ML is perfect for everything, but it's really good at doing things like manipulating trees. All right? So that's a taste of 51, and I'll hand this podium over to Steve Chong, who will tell you more about 61, but I had to put my favorite cartoon up first.
Great. Hi, everybody. I'm Steve Chong. I'll be teaching CS61, which is Systems Programming and Machine Organization. Now, before I tell you more detail about what this course is about, what it's covering, I just want to tell you a little about where it fits into the curriculum. So it's taught in the fall. It is going to be taught in fall 2011. CS50 is a prereq for the class or appropriate experience in C programming. So all of you guys here are appropriately qualified to take CS61. For CS concentrators, CS61 is a semi-required course. You need to take 2 out of 3 of 50, 51, and 61. And for those taking CS as a secondary field, it does count as one of the 4 half courses to satisfy the requirement. So CS61 is an introduction to computer systems. It's not intended to be an advanced course. So it's relevant and applicable to all comers. You don't need to be a CS concentrator to get benefit from this course. And really, it does set you up for taking later computer science courses as well, but there's a lot of benefit just in and of itself. So what is CS61 about? To me, CS61 is really about answering the question, what happens when I run a program? So that is, from when I write my C program, when I compile it, to when I execute it, what is going on? What is making that program work? What is making it do what it's doing? What affects its performance? What makes it run fast or run slow? What affects its reliability, its robustness? Now, in order to answer these questions, we really need to delve into the working of of the machines, to get under the hood, if you will, at a level that you've been touching on with CS50, but we dig deeper in 61. So there's a whole lot of computer science concepts that, in order to really understand, to really grasp, you need to understand how the machine works, what the machine is doing when it's executing your program. This includes operating systems, databases, compilers, processor architecture, networks, and so on. But in addition, having a good understanding of the machine and what it's doing is important just in order to be a good programmer. In order to write programs that are robust, that execute quickly, and that can be run on many different machines, that are portable. So, for example, if you're in your lab writing some code to analyze some data that you've gathered from your experiments, how quickly are you going to be able to perform this analysis? How easy is it going to be to run this program, this analysis, on different machines? You need to understand how computers work in order to answer these questions. So in CS61, we cover a variety of material. We answer this question, what happens when we run a program? We learn how computers work by examining how machines represent computer programs at the machine level, how we compile C programs down to this level, to this assembly level. When we execute a program, when you type in a command on the command line, what is going on? How does that program go from disk into memory to being instructions that are actually telling the computer what to do? We touch on how memory of various kinds affects the execution of your program. Caches, heap, stack, these are concepts that you've been seeing some of in CS50, and we really dig down into the details in this course. We also learn about programming at the operating system level. So the operating system provides a number of services to programs, and we see about how we can go about using some of those, such as accessing files, creating processes, creating threads, communicating between different processes within a computer. CS50 isn't intended to be a high workload course. So the course is challenging, but it's not going to be a 20-hour-a-week kind of course. If you've taken CS50, if you're comfortable with programming in C, you'll be fine. You'll do fine in 61. We have one midterm, one final for the course. There are 2 lectures a week plus 1 section, which are required. And other than that, there's 5 assignments, and that's it for the assessment of the course. And really, the assignments are the funnest part of the course. There's a number of your TFs, current or previous students of CS61. Have a chat to them about it. But really, the assignments get you into the nitty-gritty details of x86 assembly, of writing, for example, implementing malloc, managing memory in the heap that I know you've been doing in some of your assignments. Okay, so I want to give you a small flavor of some of what CS61 is about in the remaining time, to give you an example of a reason why it's important to understand how computers work. And to do that, I want to tell you about Ken Thompson. So Ken Thompson was one of the co-inventors of Unix, and he received a Turing Award in 1983 for his contributions to computer science. And in his acceptance speech for the Turing Award, he made a surprising revelation about the early days of Unix. And what he did was he put a backdoor into the program that controls the login into Unix systems. In particular, it allowed Ken Thompson to be able to access any Unix system at all by entering, for example, his username and password, Ken and the password magic. This was really helpful for debugging. If some Unix installation was having a problem, he could log in there, figure out what was going on, right? But of course, this is very dangerous, having a backdoor into the system, and you wouldn't want it to be misused or to be known about by the wrong people who could get into the system and do terrible things. So anyone, in particular, anyone who looked at the code for the login program would see that there was a special line saying, if username is Ken and password is magic, then let them in. So what could we do to hide this backdoor? So what Ken Thompson did was he hacked the C compiler. The C compiler is the thing that takes the C source program and produces the machine representation of the program to execute. So the C compiler, he changed it so that it noticed when it was compiling this login.c program. And when it was compiling login.c, it in fact inserted this little backdoor, this magic code, if username is Ken and password is magic. So great. At this point, if somebody took a look at the code for login.c, everything looks completely normal, right? It looks like a login program that's doing the right thing, nothing special. But if somebody went and looked at the C compiler, they'll be noticing this suspicious code that says, if the file I'm compiling is login.c, then do the special stuff, right? So I've hidden this backdoor a little bit, protected a bit, but there's still some suspicious code out there in the C compiler. So what do you think was the next step? Ken Thompson hacked the C compiler again. And this time, the C compiler noticed when it was compiling itself. So this is quite a profound concept, that when we write compilers, for example, when we write a compiler for the C programming language, we can in fact write it in the C programming language. There's some issues about how you bootstrap that, but you can do this. And in fact, in the early Unix systems, the C compiler was written in C. So Ken Thompson hacked the C compiler so that it noticed when it was compiling itself, when it was compiling the C compiler. And when it noticed that, it modified the C compiler to insert this code that when it noticed it was compiling login.c, would insert this backdoor. So this is pretty complicated. So at this point, we then compiled the C compiler and deleted the hacked compiler code. So now, somebody who came along and looked at login.c, the code for the login, would just see normal, completely non-suspicious code. And when they looked at the C compiler, it would also look completely all right. But there was this backdoor. And that backdoor only existed in the binary executable for the C compiler and the login program. In order to find that backdoor, you'd actually need to look at the binary executable, at the machine representation of the program. So one of the morals, and there are several, but one of the morals of this story is that computers may not be doing what you expect them to do. And I encourage you to take CS51 and fine-tune your expectations about what computers do and what they're meant to do. Now, I'm out of time. Take 51 or 61. My suggestion is take both. They're really complementary. 51, as Greg was saying, gives you a higher level of abstraction. CS61 digs into the details. If you have more questions, feel free to email me or look at the webpage for CS61. And hope to see some or all of you in fall 2011. Thanks.
All right, now that you've heard about two courses that are designed to teach you how to write better code, I'm going to talk about a completely different course which has no code in it at all. My name is Jim Waldo. I'm a professor of the practice, which means I have a day job. My day job is to write code that you actually do depend on in your everyday life. In your case, I wrote chunks of Java. So you depend on it in your everyday life. But since I actually do that for a living, they don't let me teach it. So instead, what I teach is a course, at least the one that I'm talking about today, called Privacy and Technology, CS105, which is not one that is recommended as part of the curriculum. And in fact, I am kind of hoping that I don't convince you that you want to take, because we want to keep the class small. And it's different. So the whole purpose of the class is to talk about the notion of privacy and how privacy interacts with technology. Now, this is not giving you scary notions of what Facebook can do, because you should already know that. It has to do with whatever happens to pop up in the New York Times that week. It's a great curriculum. We just read the paper, and stuff keeps coming in. So, you know, Our friends down the street at Google, it turns out, are not only mapping the street, but they're mapping the wireless networks. And oh, as they're doing that, they're picking up traffic. Is that a violation of privacy? They're not in your house. They're not looking at any but you know, the distinction between privacy and creepy is often in the mind of the beholder. And that's part of what we talk about. The question of what threats there are in the privacy era and in the kind of technology that you are using every day is the whole idea behind the class. Because when you hear about how awful the privacy threats are, the question is, are they really that bad? What is the threat? If you watch CSI, you'll find out that people can read the RFID tags in your credit cards from across the room with an RFID reader and steal your identity. Can you actually do that? Do you know? What's the technology behind RFID tags? What do they actually do? What's the physics behind RFID tags? One of the things that caused this class to happen was when I was down testifying in front of the Federal Trade Commission, telling them about RFID tags and the problems that you have in reading them, and I mentioned the inverse square law having to do with radio frequency transmission. And afterwards, one of the lawyers came up and said, "Can you tell me more about this inverse square law? When was it passed?" Now, you laugh, but these are the people that are passing laws and regulations that govern what technology can be built and shipped. And they think the notion of the inverse square law is something that could be repealed. It's tough. It's good to know what the threats are. It's good to know what privacy is. It's not at all a clear concept, and we spend some time doing that. In fact, we spend the first couple of weeks of the class talking about legal and philosophical and economic theories of privacy, because if you don't know what you're talking about, you become a politician. But you also need to do good analysis on this if you really think you're going to talk about the threats to your privacy in technology. This is a very odd class because we don't write any code. You can for your final project, which we ask everybody. We ask everybody to do a final project. Well, we don't ask, we insist. But it can be code, it can be papers, it can be policy, because part of what we talk about is not only what kind of technology can cause problems with privacy, but who should be the one ensuring that privacy is in fact maintained. Should it be you? Should it be the government? Should it be who? How do you maintain technology? How do you maintain privacy with the technology? Should we make sure that the technology is built a certain way, or do we pass laws to keep technology from being used in certain ways? And of course, that brings up the question of where. This sounds like your old journalism teacher, right? Who, what, where? But it is, in the case of privacy, an interesting question. If you are in Europe, they have a very different notion of privacy and who guarantees privacy than we have in the United States. Those of you that might be working for a company that works both in Europe and the United States now have an interesting problem. Whose laws do you follow? What jurisdiction are you going to get sued in? When Italy decided that they wanted to sue Google for privacy violations, they dragged in some of the top executives at Google to actually stand trial. They didn't show up in Italy. Does this mean that if you are going to do something foolish in your spare time at Harvard, like start a billion-dollar company, you could get sued by Tierra del Fuego? Who knows? How do we go about protecting privacy? Always a question. It can be policy, it can be technology. Sometimes it's both. By the way, the prerequisites for this course is that you are interested. We try to make sure that at least half of the people in the course are not computer science people, because we want to have a mix of technology and policy discussions. And by the way, you are not only encouraged to work in a group, you are forced to work in a group, although generally groups that we make up, not the ones that you make up. So you will probably end up working with people you don't like. This is what's called a life experience. This is a course that is different. It is not like your standard computer science course, because you will be talking about philosophical problems. You will have to learn how the Supreme Court came to decisions in certain ways. You will talk about law, you will talk about economics, oh, and you will also talk about computers, because all of these fit together in this course. Now, logistics of the course, there's 3 of us that teach it. There are 30 people that we allow to take it. Depending on the size of the currency on which the requests are made, we might let in a 31st or a 32nd. We'll see. The course meets 2 times a week. And we do it as a set of case studies. We will begin with a couple of weeks where we talk about the fundamentals of privacy. This is the philosophical and legal backgrounds of it. And then from that point on, we do case studies where we will look at a particular technology that may be threatening your privacy. We will, in fact, try to sucker you into thinking that either the technology is invading your privacy or it's completely safe, and then show you that what we suckered you into was wrong, and then change the rules again. Because the point of this class is not to teach you anything that is absolute. It's to make you think about the issues and learn how to analyze the technology and the implications of the privacy so that you understand. And so that you can read the New York Times. And when it says that there is a privacy violation going on because of some new technology, you can think about that and see if it's something you should really be worried about. And we end up every section, every 2-week case study, with a group project. Now, it's an interesting group project. We'll give it to you Thursday afternoon. It's due Saturday night. No, actually, we've changed that to Sunday night. We decided having it due Saturday night was probably a violation of the Geneva Accords. So it's due Sunday night, and it's designed to be larger than any one of you can do in that period of time. So you have to work together with others. This is an interesting concept for many Harvard students. The technology is a piece. The policy is a piece. What the remedies are, we will ask you rather than telling you. And mostly we will tell you that you're wrong. The kind of wisdom that you get from this class is Socratic in nature. You learn what you don't know. Turns out in the privacy area, that's a lot. We'll talk about the law, we'll talk about economics, and we will talk about design. Because design is often important. You can design things in such a way that it is less likely to cause privacy problems than other designs. And if you think about that, you can avoid a lot of the problems that we will be seeing. But you have to think about it up front. And as I say, mostly we will be asking questions, and we will be raising questions, and we will be teaching you to question. So as I said before, we only let 30 people in. Only about half of them can be computer science majors. So don't think about this class. Don't take this course. Really. But it is, I think, certainly the most different. And if this were Sesame Street, we'd be the one that wasn't like the others. And I think in some ways it's the most important course that you can take in the computer science curriculum in terms of the impact it has on your everyday life. Thank you.
All right, I'm Harry Lewis. Nice to meet you. So I teach CS121. I hope you've noticed that there's a numbering pattern to these courses. So the ones that require no programming are down at the bottom. The middle digit 0 we actually created just for the privacy course. This course also requires no programming because it's about the fundamental underpinnings of all of computer science. And it's called Introduction to Formal Systems and Computation. So we do math in this course, but it's not math that really depends on, that in any way depends on knowing the calculus or anything like that. It's math that any kind of college math level sophisticated student can do. It's one of the few required courses in computer science because it underpins many other courses. If you go look at the prerequisite tree, you'll see lots of other CS courses that require it. But I also have a lot of philosophy, linguistics, people interested in other areas of human knowledge also tend to take this course. And as I thought about it last night, there's really two different ways to think about what this course is about. So at one level, you can think about it this way, that there are these digital computers around, and we program them, as you've heard in the presentations on CS50 and 50, you learned from CS50 and from the presentations on 51 and 61. And there's a whole variety of technologies at the high level and at the low level about how you make computers do stuff. And there are hardware design courses about how the underlying hardware works and so on. And that what we want to do in 121 is to abstract away as much of the sort of contingent physicality and the sort of technological oddities of programming languages and processor designs and so on, and get down to the core of what it really means to be a computational process, to be a computational process, to execute a computational process, and to get a computational result in order to solve some computational problem. So it's about the formalization and the abstraction and formalization of the very notion of a computational problem, so that it's the kind of common core of all of the what's underlying all of the computer technologies that we study in all of these other computer science courses, because we have all of these computers of which this is the sort of common instance. So that's one way of looking at it. What I've drawn up there is a very simple state diagram from some process. This is actually, if you want, is a kind of a 2-bit adder. It's a thing that's it's a state system. It's got 4 states. You start in state 0. There are 2 possible inputs. These are things that change you from one state to another, A and B. The A's take you from left to right and right to left, and the B's take you from top to bottom and bottom to top. So you can sort of think of this as a way of counting whether you have an even number of A's or an odd number of A's, and also simultaneously whether you have an even number of B's and an odd number of B's that have come out. So you abstract away, lots of different ways of expressing this little algorithm, which requires 2 bits of storage, as it were, to keep track of, and you get the theory of automata, the theory of mathematically formalized computers, and that's what we do a lot with. And we do it for a reason, because once we have a theory of these kinds of mathematical automata, these formal systems, you can turn it around and apply it to solve by coding up the algorithms that analyze automata, to solve all kinds of significant computational problems. And many of the leading questions in computer science today about how effectively problems can be solved, things that you may have heard about, like the traveling salesman problem and all of these very difficult search problems, are expressible in terms of problems about these formalized systems. And there are lots of examples where the problems are not only beautifully interesting intrinsically, but also very useful in practice. So I had the honor of teaching this course to Bill Gates. I taught this course to Mark Zuckerberg. They both talked to me about their little algorithmic problems that they were working on. Gates got a paper out of it. Zuckerberg got a company out of it. Okay, Gates really did have a paper that he wrote after he took this course. So there are all kinds of neat applications that are not only intrinsically interesting, but computationally useful. Okay, so that's one way of looking at it. That's the sort of way of looking at it that says it's like physics. You observe the physical universe and you throw away friction and so on, and you get some Newtonian laws, and you can make some predictions about how the world will behave. That's the sort of classical way that we think about this stuff. But there's actually another way to look about it, what goes on in CS121. The other way to look at it is to realize that the theory of computing actually preceded the invention of digital computers. Digital computers were kind of a product of the post-Second World War period. In practice, you can argue about the details of it. But the theory of computing actually arose out of really fundamental questions about what mathematical truth is, what a mathematical problem is, what does it mean to solve a mathematical problem. So I actually try to hit all of the gen ed areas in this course in one time or another. But we certainly go back, and we actually look at the turn of the 20th century, when people were trying to come to grips with the notion of what intrinsic mathematical truth was. And we read David Hilbert's paper on mathematical problems. It begins by saying, which one of us would not want to lift the veil behind which the future lies hidden? He's trying to imagine what's going to happen to mathematics, and he lists out a whole series of problems that he wants solved. And implicit in there is actually explicit in there is some sense that, you know, there ought to be some way, if I write down a problem, to be able to figure out whether the answer to the question it states is true or false. So this is the 1900 famous address about the future of mathematics. And the part of the question that was stimulated by that line of thinking encapsulated in Hilbert's paper was settled by this fellow, Alan Turing, at a very young age. This is about the age he was when he showed that there was no possibility of developing a universal algorithm for determining whether mathematical statements were true or false on computable numbers with an application to the Entscheidungs problem, 1936. And it was only after he wrote this paper that Turing himself became one of the original creators of digital computer technology. So we'll trace that kind of, there's a thread here of the intellectual history of the subject as well as the development of the mathematical foundations of the subject. And the bottom line is that computer science is one of the few fields you can study where you can actually witness it becoming scientific. That is where you can actually see people struggling to formulate what the real questions are hidden behind all of the programming tools and hardware design tools and so on. What does it actually mean to have a scientific answer to questions about whether a certain algorithm is possible or whether a problem can be solved in a certain amount of time? So, so part of our goal in CS121 is not only to teach what you need to go on in computer science, but also to teach what it means for a discipline to become a science. Thank you.
All right, I'm here to talk about Computer Science 124, which, like CS 121, is one of the more theoretical courses at Harvard. But even though it's theoretical, or because it's theoretical, I consider 124 to really be like the core for anything else that you might do in the future of computer science. Really, we're looking at the questions of how do you solve computer science problems efficiently? How do you solve problems efficiently? And what does that even mean in this context? What are the resources that you're trying to use to determine how efficient your program is? One of the most obvious is time, something you've probably run into in this class, trying to make things run fast. But there's also space, and there's other resources you probably even haven't thought about yet, things like correctness, which I'll talk about in a second. In 124, the goal is really to try and connect the theory to the practice. Right? So part of what we're looking at is what can we prove mathematically about the performance of our algorithms and data structures? What can we say about them with mathematical statements? But then how do we take that and translate that onto an actual machine? Right? What does the theory tell us about how something will work when we code it up? So part of that means that in this class you don't just have problem sets, but you have problem sets and programming assignments. You'll not just be writing equations or solving puzzles, you'll be implementing to see how these things perform once you put them on a computer. And moreover, we'll look at some of the questions that are raised by, for instance, CS121, namely, what can we do about problems that are too hard to prove anything useful about? Okay, so you don't need to take 121 to take 124, although it can be helpful. But one of the things you learn about in 121 is there are problems that we don't have good algorithms for. And unfortunately, when you're in a job and someone comes up to you and says, I need a solution to this problem, going back to them and saying, well, that's a very hard problem and we can't actually solve it, isn't likely to get your employer to be very happy. So we have to look at things we can do in those sorts of situations. All right, so one of the goals in this class, arguably the main goal in this class, is to make sure that every student walks out with an appropriate algorithmic basic toolkit. Right? So if you're going to hire a handyman, you want your handyman to come in and look at whatever the problem is in your house and say, wait, I know that this is a problem I solve with a wrench, or this is a problem I solve with a hammer, or this is a problem I solve with a screwdriver, right? That they have their tool belt in front of them, and they know that they have the right basic tools in order to attack whatever household problem you have. And in 124, we're trying to do the computer science equivalent of that. I want you to leave that class knowing that when someone comes up to you with a problem, that you have the toolkit available to solve it. So we'll go over a bunch of the basic methods of solving problems: graph algorithms, greedy algorithms, divide and conquer, dynamic programming, and linear programming. But more importantly, we'll also talk about some of the basic ways of thinking about and understanding problems. Modeling. How do you take a problem statement in the real world and turn it into something abstract that you can think about and compare with other problems that you've solved before? And key to this will be the idea of reduction. The idea is that when a new problem comes to you, you should think, how is this like the other problems I've seen before that I know how to solve? In particular, how can I avoid reinventing the wheel? How can I just take the wheels or the tools that I have and apply them to this problem? Right. So for those of you who are thinking, handyman, I don't want to be a handyman. That's not what I want to do computer science for. I want to learn about, the intellectual ideas behind computer science. Don't worry, we're not going to ignore that. Some of the main themes in Computer Science 124 touch upon the basic cornerstones of computer science, some of the most basic ideas that continue to grow and expand today. One of them, the idea of using randomization. Turns out that by flipping coins, you can come up with better algorithms, better in the sense that they're more efficient, better in the sense that they're actually much easier to analyze. So we'll be looking at the basics of how to use randomization to help you in algorithms. Approximation algorithms. I mentioned before that correctness itself is a resource, right? Maybe for a really hard problem, rather than spend a long time trying to come up with the exact answer, you'd be happy to come up with a very, very short amount of time if it got you within 1% of the right answer. Certainly that's true with how you study, right? You'd much rather spend a few hours to get a 99 on your exam than all week to get 100, right? So we look at approximation algorithms here. You don't always need to get the right answer. Correctness itself is a resource that you can trade off against time and space and how to make use of that idea. We'll be looking at heuristic algorithms. Even though we're a theory class, I'm not tied to the notion of mathematical proofs. There are a lot of basic foundational ideas that can be used to tackle hard problems, even if they're a heuristic, even if we can't actually prove the formal things we'd like to prove about them. All right, so really, why do I think that everyone should be taking CS124? CS124 is all about the idea of how do you start with a basic problem out in the real world, and what techniques do you have, what tools do you have to apply to solve the problem. You want to start by taking a problem, modeling it, going through, seeing if you already know a solution. And if you don't know a solution, maybe you know something like it for another problem. Or if you don't know that, maybe you know a technique. Or, and what can you do? What's your toolkit? What's your chain for solving a new problem? So I think everyone who wants to actually use computers to solve problems, which I hope is most of you, would want to take this course. It's great preparation for job interviews. I think of my class as a feeding ground for the Googles, Facebooks, and whatever the next big company is going to be out there of the world. It's good if you're going to grad school. Grad school is all about solving problems. It's good even if you're not a computer scientist. If you're a biologist, a physicist, even a social science major who intends to use computers to solve problems, I think you need to know and understand these techniques. So I hope to see you there next semester or in the years ahead. Thank you.
So my name is David Brooks, and I teach the computing hardware course, CS141. What this course covers is essentially the digital logic design and the hardware-software interface in computing systems. So since I'm a computer architect, all of my talks, of course, have to say something about Moore's Law. And what Moore's Law is essentially the underpinnings for how computing hardware has scaled over the past 40 or 50 years. If we look back to the original paper from Gordon Moore, what he was showing is an extrapolation of semiconductor technology at the time, and just connecting what in this case was just 4 or 5 dots seemed to be an exponential trend in the integration capacity of computing devices. So it's actually plotting the number of components that can be integrated in a particular chip at the time. And so he saw this trend had held for about 5 or 6 years and made the wild extrapolation that this would continue well into the 70s. And it turned out it held for much longer than into the 70s. It's still with us today. And what this has resulted in is a transformation in how we do computation. So going back to 1951, looking at the UNIVAC system with something on the order of 5,000 ads per second in a package of basically the entire room, 4,400 cubic feet package. And comparing that to what you can get in 2010, we have about 12 to 13 orders of magnitude between those last 50 or 60 years. So a high-end graphics processing unit from NVIDIA, something that you can get off the shelf today, gives you about 1.5 tera floating point ads per second. And so what this means is that the amount of computation has grown, and luckily the demand for computation has really kept pace with this. There's computation in pretty much everything, as Greg mentioned earlier. And in particular, this curve that I'm showing now is something that's of great interest in the current climate. What this is plotting is the server footprint for a large internet data center company, namely Facebook, and the number of servers that they've acquired over the last couple of years. And luckily, we have Moore's Law giving us exponential increases in computing capability because we're seeing exponential increases in computing demand from these types of companies. So at the high end, we're seeing companies like Facebook pushing the bounds of high-performance computing in these data centers. At the low end, we have the low-power computing that we all have in our mobile cell phone devices. So going back to that UNIVAC, which used 125 kilowatts for 5,000 ads per second, what you have in a typical MP3 player is something like a Sigma-Tel STMP processor. This is a picture of one of these MP3 players. And if you look inside that, it's got a small little microcontroller that consumes milliwatts. Essentially, it's low enough power that you can run one of these devices for many, many hours on just a AA battery. And the interesting thing about this device is that the core, the microprocessor inside this device, is actually very similar to what you'll end up building at the end of your CS141 project. It's a little RISC core and a DSP for audio decode. So let's talk a little bit about what you'll learn in CS141. The course really hits on 3 major features, 3 major pieces. The first is digital logic design. We start with Boolean algebra and the basics of Boolean logic. We move through the process of learning how to design arbitrary logic functions using AND gates, NAND gates, and NOR gates. And then we move into larger components. So if you think about the types of computation that are being done in a microprocessor, we need arithmetic operations. So we teach you about adders. We teach you about multipliers. We teach you about shifters and other core computational blocks inside a processor. At the same time, we need to have state control. So we teach about finite state machine design, and at the hardware level, how you actually implement these finite state machines or finite state automata inside a microprocessor. And so the digital logic design piece of the course, I'd say, is about the first 4 to 6 weeks of the class, just teaching fundamentals of digital logic design in terms of the basic concepts that you need to implement something like a microcontroller. The second part of the class looks at computer organization. And what computer organization covers is how you take all those components, the adders, the multipliers, the finite state machines, and you put them all together in blocks to form a microcontroller. So on the right here, we have a die photo of a high-end Intel processor with lots of different cores. Inside that core is all the different blocks that I'm talking about: adders, multipliers, shifters. And computer organization is understanding the principles of how you take all those pieces, combine them together to actually have a working microprocessor that can take instructions from your software program, execute, and actually execute the code that's coming from your high-level languages. So at the same time, as we're teaching digital logic design and computer organization, we also teach you a new programming language. This programming language is called Verilog. And the goal of Verilog is not to program software, but to program hardware. So you can think of this as the equivalent of C for hardware designers. A lot of hardware design is done in Verilog because it's a very nice high-level abstraction to designing hardware structures. And so Verilog is a way of laying out your digital logic design in the context of some larger computer organization in order to design a microprocessor. And the course is nice because I doubt that many of you have looked at Verilog. Probably no one has. And with the class like this, we pretty much teach you everything you need to know about digital logic design in Verilog when you come into it. So one of the nice things about this class is, of all the computer science classes, this is the only one that has a hardware lab. There's actually a lab in the basement of Maxwell Dworkin where you'll go once a week and you'll play around with hardware. It's a computing hardware class, and so we need to actually have you use hardware. And this is the board that you'll get when you sign up for the class. We actually give everyone one of these to take home with them so you can connect it to your computer. You can program this board, and you'll use it in your lab assignments. And the culmination of the class, as I mentioned, is a little RISC microcontroller that you actually will build in Verilog and run on this board and be able to execute some software. So what does this board have? It's actually a very powerful board. It has an FPGA here, which has 1 million gates. And 1 million gates is roughly the equivalent of, let's say, again, a small little microcontroller that you would see in something like the iPad Nano or the smallest iPod devices. It also has a fair amount of memory, 32 megabytes of memory, and 2 megabytes of flash where you can store the code that you want to execute on this. It's very fully featured. It's got a VGA port, a keyboard mouse port, so you can actually log into the system and interact with it, see what's going on with the VGA port, connect through the keyboard and mouse port. And it's got a prototyping header, so if you want to add additional hardware features to this board, you can go ahead and plug them into that as well. So using this board through the course assignments, you'll be able to learn how to program an FPGA using Verilog, how to interface with all the other pieces of this board, and essentially understand how the software actually runs when it gets to the hardware level. And so that's a really nice experience coming from the more theoretical and software level classes. With this class, you get your hands dirty with some of the hardware and provide some of the foundations for later classes in this area. So just to wrap up, a little bit of a fact on CS141. The prereqs for the class is essentially CS50. Again, we assume you know nothing about hardware design because most of you don't. And we'll teach you everything you need to know about Verilog programming. And while the principles have a flavor of what you've learned in programming C and other languages, it's a very different programming experience because you're thinking in parallel when you're designing hardware. And so Verilog forces you to think that way, and we'll illustrate that through the class examples. This is a fall term class, so it'll be offered next fall. And it's a nice class because it leads into some of the other hardware design classes at Harvard. Computer architecture, which is taught after that, CS146, and the digital VLSI design if you're interested in getting into the lower levels of the design process. So if you're more in the electrical engineering side, you'd probably be interested in CS148. If you're more in the computer science side, you'd be more interested in CS146. There are also a lot of other grad classes that follow off of these two classes. That's about all I have to say for CS141. I'll hand it over to.
Hi, my name is Mariah Meyer, and I'm not Hans-Peter Pfister, who teaches CS171, but I am a postdoc here in SEAS, and I work with Hans-Peter. So this is actually what Hans-Peter looks like, and more importantly, this is what he looks like when he's visualizing something. So 171 is about data visualization. And visualization is really about this idea of conveying information through visual representations. And we see visualizations all over the place today. So why do we care about visualizing data? So as many of you, I'm sure, are aware, we're really in this information explosion right now. This information is coming from sources like Facebook, your social network. It's coming from places like your healthcare records, from government agencies. Data is all around us in our society. And it's also coming in large part from the sciences and engineering. Science fields are really experiencing this industrial revolution of data through sensor networks, through large-scale astronomy projects, and in biology through high-throughput sequencing. So basically, we're surrounded by tons and tons of data. And so how do we make sense of all of this? So here's one way you might want to do it. Load your favorite data set up into Excel. Does anyone see anything interesting in this? It's actually a trick question. I have no idea what's in this. And it's really, really hard to make sense of relevant patterns and make any sort of insight about a data set looking at tabular data in this way. So there's this famous quote by a researcher named Donald Norman that it is things that make us smart. And throughout history, humans have been putting information into artifacts that help us make sense of the world around us. If you think of our brain as a computer, we have a very powerful CPU, but very, very limited amounts of RAM. And so by putting information into artifacts that we can then look at, it frees up our cognitive abilities to do higher level tasks. So visualization is really a tool that helps us to think, and it reduces the load of our working memory. It offloads cognition and instead allows us to use the power of our human perceptual systems to make insights into data. So 171 is really a class that is all about giving you skills to be able to do this. The things that you'll study the principles of effective visualizations, what are the design principles involved with effectively communicating information. You'll learn how to gather data using Python, so you can go and scrape data that's interesting to you from places like the web. You'll also be implementing a series of interactive visualizations using a programming language called processing. And there's a series of programming homeworks, in essence, to get you up to speed in processing. And there's also a final project where you get to pick some sort of question that's relevant to you, get the data, and design a tool to communicate that information. I'm just going to show you a few screenshots from tools from some of the former students in this class. This was the students really loved this one. This was by Samir Paul and Jesse Rader. And what they did is they managed to get all the data from the Q guide, or from the reviews of students, and design this tool that allowed them to filter classes. So you could say, look for all the classes that had really high ratings but really low workloads. And so this was a tool that a lot of students really wanted to get their hands on. There was another interesting project last year by Jason Gao, and what he did is he was able to look at the environmental impacts of different buildings on campus by looking at their energy usage. Naveen Sinha, who's actually now a graduate student in SEAS, he's a foodie, and he was really interested in the restaurant reviews from the different sources here in Boston. So he developed a tool to compare and contrast how different reviewers rate restaurants. Karen Hansen is actually a distance education student. This course is also taught over the internet. And she was actually in the admissions department at Berkeley. And so she was able to get a hold of some of their admissions data and developed a tool to start to explore some of the relationships in there. And another one that I thought was really fun was a student who is a grad student in biology here. And what he did is he was really interested in the publication records of all the faculty members in his department. And so he wrote some code to scrape all of their information from their CVs. And he came up with some really interesting ways to sort of compare the productivity of the different professors. And he found some pretty interesting things in there. So no one has yet to do this for the computer science department, so possible final project. So here's a list of the different types of topics that you'll study in CS171. And sadly, Hans-Peter wasn't able to be here today, so you didn't get to hear how he engages students. But from personal experience, I took a class from him years ago. And it was actually that class that largely inspired me to go and pursue a PhD in computer science. So he's a very inspiring teacher. And CS71 is a very fun class where you get to think about aesthetics and design, think about what are interesting questions to ask and how to answer them. So I encourage all of you to consider taking it. Thank you.
My name is Krzysztof Gajos. I teach CS179, the design of usable interactive systems. This class has been taught once so far. This year it will be improved based on what we've learned last year. So I wanted to start by reminiscing about my college days when an amazing thing happened in computer science. A company called Google emerged. And it was incredibly exciting because it solved a very important problem. It solved a search problem, which at the time was a very big problem. And they were the first ones to actually solve it really, really well. And as a consequence, now Google is a really big company. And Google is an example of incredible success in computer science. And it's often also shown as a company that did something amazing and something incredibly difficult. What I'm going to argue to you is that Google actually solved something incredibly trivial. It solved the problem that somebody else has figured out. Somebody else has asked the question, and Google only came and solved it. And you may be thinking that search, that internet search, is actually an obvious problem. Like, how hard do you have to think to figure out that you need to search the internet? Well, it turns out that you have to think pretty hard because this is not what people did at the beginning. As easy to use as the phone book. Isn't it the right way to search through the information on the internet? This is what we used to do. Then it took somebody to figure out that we can actually take the phone book onto the internet. And then it took another genius to realize that instead of people putting in the information to the phone book, we can actually scrape it automatically. And then it took another genius to figure out that we don't have to use supercomputers, but we can actually use efficient farms of scalable computers to do it efficiently. And then, at that point, people realized, all right, now we've solved these types of problems. The last little bit is remaining. We would like to get something useful back. And this is what Google has solved, but somebody else has asked the question. In contrast to Google, consider these enterprises. What kind of a well-defined question, what kind of a well-defined problem did Wikipedia address? Did we know that we wanted teenagers to write encyclopedias? Twitter, did we know that we wanted to communicate in messages of 140 characters? Somehow, these guys have figured something, they have managed to uncover a latent need that was incredibly potent, and they were able to build on top of that need. Now, the question is, how do you figure out those very important needs that nobody is able to articulate? And this is precisely what 179 is about. In the first several weeks of the class, you will actually learn how to discover latent and unspoken needs in the society, needs that are just so fundamental that people do not even realize that they have them. Seriously. Now, the problem with just having a need but not having a clear statement of problem is that you have to figure out what style of an approach is even appropriate. Is the appropriate thing to build a technical solution? Is the appropriate intervention to introduce new legislation? Like, how do you even go about addressing a need? Now, once you have some idea of what are the plausible ways, how do you very quickly figure out which ones of them are most promising without spending too much time on them? So you will learn skills for generating large numbers of plausible ideas. You will learn skills for very quickly weeding out the bad ideas and collecting the nuggets from the good ones. You will learn how to very quickly design prototypes and how to design solutions for people who are very unlike you. you can introspect about your own needs, and you can probably design pretty good things for other Harvard students. But will you be able to design something for somebody who's illiterate, or for somebody who has a very different information needs than your own? And finally, you will acquire powerful tools for quickly evaluating whether a particular approach or an idea is plausible and whether it's making an impact for an organization. And just like in Jim Waldo's group, you will learn teamwork. The problems that we'll be addressing in this class will be large, will be substantial, so they won't be solvable by a single individual. So most of the class will be spent on working toward a large team project. The class will meet twice a week on Mondays and Wednesdays. We are the only class in CS that actually has studios where you will present and critique each other's work, because it turns out that one of the essential tools for being productive in a creative enterprise is to actually gather critical feedback from knowledgeable peers. So we will learn that skill as well. Oh, and by the way, we will also program. You will be building solutions that for iPhone and iPod Touch web applications. So you will learn JavaScript, CSS, PHP, SQL, and a whole bunch of other languages, because the way we do web programming right now requires a variety of tools to cooperate together. So one last reflection that I wanted to add here is that of on the nature of computer science. If you had taken computer science with anybody other than David Malan, this might have been your idea of what your future looks like. And indeed, many people think of computer science as a lifetime in a cubicle and programming. But we may be forgetting that programming is just a hammer and chisel of our trade, and you have to be darn good with that hammer and chisel. But ultimately, computer science is an incredibly powerful intellectual toolkit for solving real problems in the real world. So I just want to finish off by showing you 4 examples of problems, real-world problems that get solved with computer science, but actually do not require a lifetime in a cubicle. Addressing healthcare needs in Tanzania. It turns out that you can improve the reliability of record keeping and record acquisition with appropriate software-based tools. Humanitarian landmine detection. One of your colleagues, a student who graduated last year, did his senior thesis on developing a tool that enables deminers to make better decisions about whether the object that they are detecting with a metal detector is a landmine or a piece of harmless debris, such as a piece of wire or a bullet shell. We are building tools that enable severely disabled people to communicate with others and to control their environments just with their thoughts. And software tools have been used to enable rural Indian villages access to financial resources through properly monitored microfinance situations. So I believe you should take 179 if in your future you don't want to just implement other people's ideas, but you actually want to have part in creating the ideas that your company or your enterprise will be working on. This class will give you skills not only to design, but also to communicate with designers and to evaluate designs, and also to manage a creative team. So yeah, see you in the spring.
That's it. Thank you so much to our guests. Quiz 1 on Wednesday, grand finale on Monday. See you then.